Please bear with me. You no longer need to bear with me. Mad for quite a while. I legitimately feel like I seriously... The internet can totally see you right now. That's what that says. I doubt it. Have you bared with me yet? Or have you not? I'm gonna guess that you have. So because of that, I will now do this, which is a thing I've been attempting to do for a while, and I'm gonna be doing 25 vector series. First of all, I need to get my list of vector series I'm going to be doing, because I'm not just going to be doing completely random functions off the top of my head. So, first one. Before I get started, I'm going to say some things I will be allowed to drink water during this stream. 1. Alright, x squared. This is going to be quite easy. So now we can take the graph of x squared like this. This is going to be 1, 1. This is going to be 2, 4. And this is going to be n, n squared. Alright, so now what I can do is I can make a function table. Now, 1, 1, 2, 4, 3, 9. N squared. Now that we have made this function table, what I'm going to do now is I'm going to represent this in terms of a vector. So the vector's x component is going to be the x value. The vector's y component is the y value. But the thing is y equals f of x. So that means in reality this is equal to, you can use the formula. Alright. So x is going to be this. X is going to be this number, which is n. But in reality, we should say x. Or should we say n? Yeah, we should say x. So this is going to be our x value. So x is our x value. So it's going to be equal to x squared, which is just x squared, plus f of x, which is equal to y. So it's going to be x squared squared. And we know x squared squared equals x to the 4th. So x squared plus x to the 4th is our solution. Oh, don't forget nxy. That's oddly similar to tensor notation. Now let me just go ahead and make sure that this live stream is working correctly. Yes, it is working correctly. Alrighty, so now that we have done that, I will now do the second function on our list, which is absolute value of x. So, where should I put this? There you go, I guess. So we're going to have now, there are actually 2 ways we could do this. We could either do the impure or the pure solution. We're going to be doing the impure solution because that's more precise. So the impure solution, we're going to take the graph like we just did. 1, 1, 2, 2, negative 1, 1, negative 2, 2. So this is our graph. Now we can draw a function table. we should actually really start at negative x. 0, 0, x, x. Now, we have done all this now. What I'm going to do is something that's kind of unusual. And I'm going to be, the thing is, I'm going to be this-ing it. Square root of x squared, because it's still x. After all, negative x squared equals x squared plus f of x squared. F of x squared is going to be absolute value of x squared. Now what I'm doing is I'm going to be assuming that this is only for positive real numbers, so this is actually just x squared. So that means you're going to have absolute value square root of 2x squared. Which, what we can do is we can split this up into two things. Square root of 2 times square root of x squared, which is going to be equal to absolute value of x times square root of 2. This is our pure solution. But the impure solution is what we're after. So what I'm going to be doing is I'm going to be moving this over there, and then I'm doing the impure solution. So, absolute value of x times square root of 2. So I'm going to be using a fundamental theorem that you probably don't know about. It's basically, if I'm writing this in logic and writing this in notation as if you are extremely familiar with mathematical logic, and I've taken 58 courses on it. But I'm going to do that right now. So I'm going to be writing this theorem. After all, I'm waving my hands, which means I'm a physicist. Well, I'm going to be writing this theorem, right? The theorem says, if I recall correctly, if fx of x implies n times g of x times some function g of x, then f accent of x equals g of x. If and only if f of x is not periodic. At least I think this is what the theorem says. But this theorem says that if you try to find the vector series expansion of a function, and it gives you n times some other function g of x, then this means that the vector series is equal to g of x. Now, basically what this means is we neglect the factors. And I might be like, where did I derive the theorem? Well, I actually didn't derive the theorem from anywhere. I just thought it would be good for, the purpose of approximating exactly. So we can neglect this factor because of the fundamental theorem, and we get absolute value of x approximately equals absolute value of x. Now that is our second function. That's our second vector series expansion. Basically, any function that has any jagged edges, not any jagged edges, but a function that is just a series of straight lines. So, and if a function has straight lines in it, if a function is only straight lines, then remember this, okay? Its vector series expansion is itself. Next function, sine of x. This is one I was definitely not looking forward to, because it takes me quite a while to do this, because function tables don't really help us out so much. That's the graph of cosine x. Wrong graph. Because, at 0, sine of x definitely does not equal 1. Better graph. Now, what I'm going to be doing is drawing a function table. Here we go, x and f of x. Now, x equals pi over 2. I literally don't know. Pi over 2 is about here, and that's 1. Pi. Here, 0. 3 pi over 2. Nope, 2 pi. 3 pi over 2. 1. Wait. 3 pi over 2. Oh no, it's actually negative 1. So it goes 1, 0, negative 1. 1, 0, negative 1, 0, negative 1. Okay, then what's next? 2 pi, I think. 0. So this is not helping us, because you see, there's no good pattern in which there is a pattern, but the thing is, unlike the function x squared, which we had earlier, with x squared, we could just represent that in terms of vector magnitude. Let's do that now. So we're going to do x squared plus sine squared x. Keep in mind that the informal definition is square root of x squared plus f of x squared. But that's not what I'm trying, that's not what really matters, because this graph. Okay. Let's go on to Desmos and see what this graph is, because I legitimately don't know. Okay. Let's do the graph. Square root of x squared plus what? Sine of x squared. Plus sine squared x. Sine squared x. This is what we get, which is not a very good approximation. So this is what we would call the pure solution. But the thing what we say, okay, this is what we call the pure solution. And it's also the impure solution. But what we want is what we call the periodic solution. So we're going to have to use our good old friend, triangular waves. Or I'm going to say the triangular wave theorem in order to solve it. Now, I don't know if this is the stick of chalk I was using, but anyways, triangular wave theorem, what it does is we have a function like this. So what we can do is we can approximate it with triangular waves that go like that. Now that's technically still a vector. That's technically still a vector series because it's really a series of vectors. Not as in an infinite sum of them, but it's still a bunch of vectors, which is the definition of series. Not the mathematical definition, but the informal definition. Now, if we have our good old graph, okay, if we have our good old graph here, what I can do is I can have these vectors. This is a vector, that's a vector, that's a vector. Now, just remember this. It's not useful, but remember it. This length right here, the length is equal to square root of, this length is equal to square root of pi squared over 4 plus 1. Just know that, okay, please. Alright. Now, what I can do is I can say that this is the triangular function. So, triangular wave function. This is our approximation. And we're gonna be like, what triangular function is this? Triangular wave function. Well, if you are if you're smart boy, then you would know this is actually the graph of 2 over pi times inverse sine of x. Okay, this is our approximation, guys. So now that we have our approximation, let's use our approximation skills for another function, another trig function that's also periodic. Okay, let's try cosine x. Okay, cosine of x. Okay, so cosine x, the way we do this is we're gonna take our last one. So note, I write it like this. I said in the thing, I'm not black pen, red pen, but who knows? Maybe I might be. Okay, let me check that back to the live dashboard. So I'm probably not black pen, red pen, but because I want to be black pen, red pen, I'm gonna get out a red chalk. Now, note. So I have white chalk, red chalk now. But what I'm going to be doing is I'm going to be showing you the note. And it's a pretty cool note. The note says, I'm not quite black pen, red pen at switching chalks. I can only switch them with my 2 hands. So we're going to get square root of x squared plus, actually no, wrong thing. Sine x approximately equals 2 over pi times arcsine So sine x. Now we have this. We have to remember this. But what I can do is we can also use an identity. Also note that cosine x equals sine of x minus 1.57. No, not 1.57. Pi over 2. Pi over 2 is approximately equal to 1.57. So what I can do is I can plug in x minus square root of 2, x minus pi over 2 for whenever we have x here. So you're going to get this equals 2 over pi times arcsine of x minus pi over 2. Now that we have gotten this, we can now carry on. We're gonna be done with trig functions for a while, at least I think. Yeah, we're doing an exponential function. We can stop using these weird periodic techniques I've taught you and use better, more efficient techniques for exponential functions like this one. We're gonna be using the exponential function that all of you guys know and love. It is obviously for e to the power of x. Now, what I can do with this, I am acting extremely energetic for no reason. I can take the graph of it, and guess what? This is not periodic. Now, because it's not periodic, that's a good thing, but what I'm going to do is I'm going to draw a function table f of x. Okay, 0, 1, 2, e squared, 3, e to the third power. Now I can use this function table for our advantage because I can use the formula from earlier. Square root x squared plus f of x squared. Now, because, as you can clearly see, what am I trying to say? Alright. We're going to have square root of x squared plus what? Well, what I'm going to be doing... squared. So basically, I can... because f of x equals e to the power of x, this is true. I think this is only not true when we're dealing with periodic functions. Oh yeah, I forgot. nx, y. So now that we've done that, we're going to be moving on to the fifth function. I think. Or maybe the fourth function. Let me see. Sixth function. Okay, sixth function. We're going way too fast. Square root of x. Let me see how long this has been going for. It's been going for about 20 minutes. Okay, now that I know for how long it's been going, let's continue. 6. Square root x. Now, this one is actually one that's a bit hard because I honestly don't know. So, let me try doing that. Wait a minute. We already have the one for x squared because that's a good thing, you know? Because that means we don't have to do any function tables. What I could do is because, keep in mind, okay, note, if f of x equals x squared, then f inverse of x equals square root x. Now what I mean here is I mean that the inverse of x squared is sine x. So that means sine x square root x, which means that our inverse of our approximation should be the approximation of sine x. Square root of x. So our approximation now we're not going to reuse an xy's here, but what I'm going to be doing is I'm going to be using however you find the inverse of a function to find the inverse of a function. Now, what am I going to do here? So, I think I can square both sides. X squared equals y squared plus y to the fourth. Now what I'm going to do is I'm supposed to isolate y, right? So if I recall correctly, I don't want to. I'm supposed to have y on only one of the sides. So let's divide both sides by x. I don't know. So if we're gonna have, if I recall correctly, if I know basic exponent rules, I can do this. So I'm gonna say we're gonna have x equals y squared plus y to the fourth over x. Now, you know what? This wasn't a good idea. I'm not gonna do this. I don't know how to find inverses of functions. Now, let's go back to the original square root of x. You're gonna have to use function graphs and function tables. So 0, 0, 1, 1, 2, square root of 2. So I'm gonna now function table x f of x. So 0, 0, 1, 1, 2 square root 2, 3 square root 3, 4 square root 4, which is 2. So yeah, cross it off, it's just 2, 2. Alright. Wait a minute. I think I have something. I think I'm onto something. Because if you recall correctly, square root x equals x to the 1 over 2 power. What I can do is I can use our formula, and I can square this. And we cross those off, and we just get x. So square root of x, so square root of x squared equals x. I already knew that, but I just remembered. So you're going to get square root of x squared plus x, which probably is the correct answer. Probably not, you know. I'm not going to go on Decimos until after this to see if I made a horrible mistake, which I probably did. We had a quick break from these, but we're going to have to return to periodic functions. Next function is sine of 2x, I believe. We're going to go into more crazy trig functions later. I almost said earlier. We're going to be doing hyperbolic trig functions. That's a warning. But good news, because some of the hyperbolic trig functions are not periodic. I think all of them are not periodic. Not periodic. Alright, sine of 2x. Here we go. So, okay, let's draw a function table. I have no idea what the graph looks like, but I'm going to draw a function table. Pi over 2. 0. 2 pi, 3 pi over 2. What is sine of 2 pi? I forgot. It's 0. Okay. Now, 3 pi on 2. Square multiply by 2. 0. So it seems like this function's always equal to 0. Am I doing something wrong? Is sine of 3 pi not 0? It's 0. I think probably. So, am I missing something? Or should I be using other things? Should I be potentially trying other multiples of pi? I could be trying pi over 4. That's a good idea. Thanks, me, who said that. So what I can do is I can, 2 columns, x, f of x. Now what I can do, pi on 4. Here we go. Pi on 4 times 2. That gives me 2 pi on 8. Which is also equal to pi over 4. Oh no, just 2 pi on 4, which gives me pi over 2. Now, sine of pi over 2, I forgot what it was. No, yeah, it's 1. Now if I do pi on 2, I get 0. Pi over 8? Well, that wouldn't really help because I forgot. Is sine of pi over 4 square root of 2 over 2? Or is it not square root of 2 over 2? Who knows? I don't. That's the only thing I know because I didn't memorize the unit circle. Now, wait, our input's 2x, which means in this case x would equal 2x. So maybe I could go back and do this of arc sine of 2x. That's my answer. I forgot parentheses. Okay. Now that we've done that, let's go to our next function, which is not periodic. It's x to the power of x. We're going to be doing tangent of x next, so warning. We're going to be using more periodic techniques, okay? So x to the power of x. Here I go. So x to the x. Y'all know the graph of x to the x. I don't know what it looks like. I think it looks a bit like this, but I don't know. Okay. X, f of x. Here we go. 1, 1, 2, 4, 3, 27, 4, 256. 256. Well, this isn't periodic, which means I can just use my formula. Square root x squared plus. I had an idea. Maybe I could use this formula for the square root. So 2. Square root of 2. Let's try square root of 2. So that would be square root of 2 squared 4. Square root of 4 plus 2. Square root of 6 would be my approximation for square root of 2. Yeah, that wouldn't work out too well. So, I'm just going to mark that as wrong for now. But let me just try this. Plus x to the power of x squared. Let me just try this for 2 squared. 4 squared. 2 squared. Square root of 2 squared is 4. Square root of this. This is 4, but 4 plus 4 squared 16. Square root of 20. It's my approximation for this. And if I recall correctly, in my video where what's it called? In my video about, in my unlisted video, about vector series, I think I said square root of 20 is approximately equal to 4, I think. Let me see. I think. So, yeah, 4. Okay. Enough of that. Let's move on to the more hard one. So one that's so hard, I literally cannot do it without using other rules that we have used in the past. Tangent of x. Now, we're going to use an identity, so... Oh, I forgot. No. Tangent of x equals sine x over cosine x. So, we're going to be using this theorem. We're going to be applying this, so it's equal to 2 over pi. We're going to be using our approximations. 2 over pi arc sine x over 2 over pi arc sine x minus pi over 2. Approximation, nxy. I keep forgetting nxy. Alright, now we've done tangent x. Let's do inverse sine x, which is not periodic, which is good. But speaking of which, earlier I think I said that I'm allowed to drink water during this thing, so I'm going to be doing that now. I've drank water now. I'm not black pen, red pen. I've been doing this for about half an hour now. But anyways, 6. 7, I mean. I've said 8, okay? We're gonna be doing 10, actually. 10 is arc sine x, but I'm gonna write inverse sine x to annoy you guys. So, how do I do this? Well, I'm gonna be, I'm gonna be using a function table again. Okay, now, so arc sine of 1, I honestly don't know what arc sine of 1 is. What is the smallest number that when you, so is it, is arc cosine after this, that's 17, and we're on 10, so I'm going slightly mad. Actually, yeah, to be honest. So is pi over 2, yeah, pi over 2, it's pi over 2, okay? 2 does not have an arc sine in complex real numbers. Now, 0 is pi, if I recall correctly. No, I think 0 is just 0. Now, to be honest, this won't really work out so well. So what I'm going to be doing is I'm not going to actually be drawing any function tables. I'm going to be drawing a graph now. So the graph looks a bit like this. Now, we can draw a tangent line, which is actually a secant line, I think probably. This is actually the line pi over 2 times x. Now, pi over 2 times x is approximately equal to, if you do not know, it's equal to pi over 2 times x. So now what I can do, it's actually this line, on second thought. That's definitely a secant line. So pi over 2x is our answer. As our approximation. It's piecewise. Pi over 2x if x, no, if 0 is greater than equal to, yeah, just say pi over 2x, okay. Because I don't really like those functions very much. You know what, for fun, let's just do arc cosine already. Arc cosine. This, the graph looks like this, I think. So, this is that. It's going to be pi over 2x plus 1. Pi over 2x minus pi over 2 plus 1, I think. It's going to be, minus pi over 2 plus 1. This is, I think that's what it is, at least. Well, okay, let's do 12 now. 12. Don't stop me now. 12 is 1 over x, the reciprocal function. Well, we all know that the reciprocal function, drink more water. You all know the reciprocal function, its graph looks like this. Yeah, but it doesn't really matter. We're going to draw a function table. So our function table, 0, plus minus infinity. Okay, 1, 1. 2, 1/2. 3, 1/3. It's not that hard. Now, well, the thing is, let's see if this works. So, you have a vector, okay? Its magnitude is x. Oh, it goes x and x, and it goes 1 over x and y. So, let's try 3. So, it goes 3, 1/3. Yeah, anyways, it's square root. This is our approximation. But if you want, I can prove it. Let's do 4 1/4, which is actually more down here, so 1/4. Vector there. That's good, I think. Alright, so now we've done that, okay? By the way, I'm going to say that I will probably, just probably, do inverse vector series soon. And then differential equations with inverse vector series in them. Just call them vector differential equations. 13. Oh no. We skipped 11, by the way. Okay, 13 anyways. I mean, I actually didn't, but here we go. Syntax. So, syntax. Graph. That is what the graph looks like. Now, I'm not going to tell you what the graph is. I don't know what sine of I is, but if I recall correctly, sine of I is the same as sine of... Yeah, I don't know. Well, anyways, don't function table this. This function, it looks oddly similar to x cubed. So what I'm going to do is I'm going to treat this like a power function. Okay, so because we can treat it like a power function, you know, this is not periodic, so this. There. That's my answer. Coshacks now. Cosh x. Cosine x, if you prefer. Now, what does the graph of cosh x look like? Function table. Let's just, I don't know, square root x squared plus cosh x squared. There. Because I don't know. 15, here we go. Actually, 14, yeah, 14. 14, tangent x. So tangent x, or hyperbolic tangent, if you prefer. It's a function. It makes me go slightly mad. But what does tangent x, what is it? It's vector series. Now I'm going to see how long I've been doing because, you know. I've been going for about 40 minutes, but I've actually been doing things for about 40 minutes. If you want, I can also do a marathon of inverse. I will, because this is not going to be long enough. An inverse will take 3.5 hours, so, yeah. It looks a bit like this, if I'm not mistaken. No, it looks more like this. And it's since x over 10 cosh x, so use your rules. X cubed plus since squared x over square root x squared plus cosh square x. There, this is your answer, okay? 15, here we go. Secant x. Another one where we can just use those. Another one where we can just use those rules. Another one, but okay. Secant x. So I did hyperbolic secant x. No, that's good. We're getting to some really hard ones. We're gonna have. I think we're gonna have the gamma function in here. So just heads up, okay? So what I can do is I can say this is 1 over arc because we know. Note. Secant x equals 1 over cosine x. So we can just say 1 over approximation of cosine x. So wrong thing. 2 over pi 2 over pi times arc sine x minus pi on 2. That there. No square root sign involved. So okay, 15. We're going to be doing 25 of these. I wrote a 5 like that. Okay. 16 actually. It's cosecant. 1 over our sine approximation. Cosecant 16. It's 1 over sine approximation. No, don't square root it. Okay, no, okay. 1 over, get into chalk stick soon. This one. Actually, no, that one's broken. Okay, 1 over our sine approximation. There. Did you know that 2 teachers so far have asked me why I have a microphone? 2 of my teachers so far have asked me, while I'm doing online classes, they've asked me why do I have a microphone, and they both assume I do singing. You probably didn't know that. Okay, I think I already did our cosine for fun, so cross that one off. 18, cotangent. 1 over our tangent approximation, which, you know what that is. That's, 18. Or is it? Yeah, 18, I think. So it's going to be our cosine approximation over our sine approximation. Cosine approximation square 2 over pi times arc sine of sine of x minus pi over 2, which really that's some of cosine, but I don't care. Over. I'm really going slightly mad right now. Arc sine x. There. Okay. Get a new chalk stick. Seriously. Champions, my friend, and we keep on fighting. So yeah. Okay, I got a new chalk stick. Erase solves this. Anything is a harmonic oscillator if you're brave enough. There! Okay, we've done all the trig functions. Okay, let's do one that is extremely difficult. Let's do, natural log of x. Yay! So make me go the most slightly mad ever, but no, natural log x, okay. Now, it's, the inverse of our e to the x thing. Okay, it involves, the Lambert W function I checked. So, let's just say it's, the inverse of our plus e to the x squared of that. Did we do e to the x? Yeah, we did, okay. This, the inverse of this. So because I have no idea what I'm doing, we're just gonna leave that solution in quadratures. Actually, never mind. I'm leaving that solution as an exercise to the reader. It's not that hard. You can just look it up on Wolfram Alpha. Don't type in vector series of that because Wolfram Alpha doesn't know what a vector series is. Just what you really should do is you type inverse of that function. 20. No. Okay, it's the common logarithm. Okay, this is the square root x squared plus 10 to the power of x squared. The inverse of all that. Okay, that's my solution for that one. Alright, now it's time for one that'll make me go more slightly mad than any other one ever. Here we go. 21. The Riemann zeta function. Now, the Riemann zeta function, I really don't know what the graph of the Riemann zeta function is. It looks like the reciprocal function, but it looks like the reciprocal function, which means it actually won't make me go very slightly mad. Thanks. The graph looks like this. That's what the graph looks like. But if we want to approximate it, for positive values, just use the square root formula. This is our solution. I'm going slightly mad. Okay, 22. Okay. Alright, the gamma function. In reality, it's the gamma of x plus 1, aka x factorial. So, how are we supposed to do this? Now, yeah, we could use the square root formula because the graph of x factorial, we're only doing positive integers, okay? This. Actually, no, it's this. So, it's square root x squared plus x factorial squared. There. Alright, now we're done with the analytic number theoretic functions that'll make me go way more than slightly mad. We're doing a function that's a little more simple. It's similar to the function we did earlier, x squared to the power of x squared. I call this the Luckless function. So, the graph looks like this. That's what the graph looks like. Now, okay. I recommend someone, if you're watching this, comment saying, Project Syntechi's Slow Descent into Madness, please. Okay. Now, because no one commented that, I guess that means no one's watching. That we don't care. Okay. It's just most likely that they don't care. Alright, 1, 2, 256, 3, a very big number, 9 to the power of 9. I don't know what 9 to the power of 9 is. So 3, big. My answer. Wolfram Alpha, no, not Wolfram Alpha, Desmos doesn't accept values over 12 for this function. Because they don't converge, apparently. It's not that they don't converge, it's just that Desmos can't handle numbers that large. Now, this looks like a graph of an even function, like, I don't know, x to the power of 1 billion. So what I can do here is amazing. I can use the square root formula, which it not only it kind of sometimes drives me slightly mad. We're gonna call this that. You know, because I'm going so slightly mad, and I honestly think the inverses will make me even more slightly mad. I'm probably not even gonna do the inverses. Okay, now I'm gonna go check how long. 50 or so minutes. Okay. Okay. Back. Alright, how slightly mad will this next function make me? 24. It's probably the function that makes me the most slightly mad. And of all of them, it's literally an implicit function. Except there is a thing about it that is amazing. And it actually makes it quite easy. We're going to use the square root formula. This is f of x comma y, I guess. But we're going to say it's f of x, so we're going to say this is the same as square root x squared plus square root of x squared plus x squared plus y squared squared. Is there another square root sign? I forgot. I don't think so. Because x squared plus f of x squared, but this is f of x. Or was that for a different function? Okay, this all equals 1. If you want, I can... Yeah, I'm going to expand this as well. Bonus problem. This is square root of x squared plus 1. Okay. 25. This is our final one. Okay. Okay. X to the x to the x. Graph it. It's this, I guess. And this, it kind of looks like it would be a power function. So, okay, use the square root formula. Square root of x squared. X to the x squared. Okay. What's that for? That now means I can take a break. But the thing is, this break, it won't last forever. H. This trick is going to be quite short. Because there's a break will not. Oh, that is what I just said. So, I'm going to erase all of this. And because you actually, I wasn't lying, I am going to go as slightly mad as possible. And my camera, that happened. Which is actually a phone. Don't tell anyone. I don't have a tripod. You should all know that. Okay. Well, anyways, let's do this. Inverse vector series. Take a break now. In the meantime, let's play some royalty-free music. Okay. Okay. Yeah, to be honest, I have literally no idea how I can do this because, I'm using my phone to record this, but I have no idea how I can, actually... Yeah, I'm just gonna play this, I guess. You probably cannot hear me at all right now. You cannot hear this at all right now, but... in the description, it says music, the Fat Rat time lapse. Okay. Here we go. Play it. Okay, we're done because it's not copyrighted. It's just I didn't want to go any more slightly mad.
This one. Look at it. Okay. No, don't bother.
Ignore what just happened because I've gone way too slightly mad today. Gonna see how more slightly mad I can get today by doing inverses. Okay. Gonna be doing them in reverse order, by the way. How long have I been going for? Counting the elevator music, guys. I'm going for about 1 hour. But change the description into that, and I'm going slightly mad. Okay. Now that we've done that, okay. I know I'm starting to develop on it. It's probably because I've gone way too slightly mad. So, okay, let's do these inverses. 1 over 25, because you know the multiplicative inverse of 25. Okay. You might not be going very slightly mad today, because maybe these are way easier. No, they're not, me. Okay, here we go. Now, what we have to do is we're going to do a bit of partial fraction decomposition. Just kidding, we're going to be doing something similar to it, though. So you write this in the form, so g of x equals px to the x to the x. Okay, now at this point, I can rewrite this in the form equals, I have to remember, okay? This is going to be quite hard, because x to the x to the x is pentation. It's tetration. It's tetration. It's also pentation, but don't forget that. It's going to be quite difficult, because this function is not algebraic. X squared plus c squared. So what I'm going to do is solve for c, and it's equal x, okay. Square plus equals x to the x to the x subtract x squared. This, we're gonna, y, okay? G squared, call it g squared. Okay. So, yeah, not to be confused with this g. No, not 9.86, that's pi squared. 9.81, not this g, this is a different g, okay? Pi squared does equal g, so it's 6, if you prefer. Okay, now it's not this g, guys. It's g of x, the function. C squared equals g squared minus x squared. X squared c square root g squared minus x squared. Okay. It equals square root of x squared